Today is what I like to term note card reaction day. This is a day where I kind of just list off kind of a whole bunch of semi-related reactions at you, all with the eye towards increasing your number of note card reactions that someday we're going to be using in synthetic protocols, probably mostly in second and third term. They're all pretty important reactions, but I tried to list kind of the most important first, and then I kind of work my way through some of the other ones. I will say that the majority of this list, I would say down to number 3 here, are all syn additions. We know a little bit about anti versus syn additions and the fact that they have some really particular stereochemical outcomes. So you'll kind of see that as a general theme, but for the most part it's going to feel like kind of disconnected information that I'm just kind of listing at you. Yay, fun! So the first thing we're going to talk about is the peroxy acid reaction with alkenes. These form epoxides, which are going to be a really important synthetic intermediate for us, hence the number 1 position here. Next thing we're going to talk about is the ability to cleave double bonds, cleave alkenes with ozonolysis, and also we'll talk a little bit about the KMNO4 reaction. Diol formation, specifically bisphenol diols in this case, with osmium tetroxide. And then what we're going to do is just kind of have a general discussion of where I should kind of be aware of some kind of oddball things about having a dilute acid versus a concentrated acid. And what really, like say on the homework, if it says concentrated H2SO4, how might that be different than dilute H2SO4? And we'll just have kind of a general discussion in there. So if you'd like to fast forward to any one of these throughout this presentation, feel free. So one thing I try to do in each one of these is to write the most common reagent for this particular general class. So in this case, I have this thing called MCPBA. It's metachloroperoxybenzoic acid. We don't really care too much about the acronym, much like we're in the Army, and we just kind of have to know what the acronym is used for, as opposed to knowing what each individual little part is. It's going to be kind of a common thing here as we memorize some of these silly note card or witch's brew type reactions. It turns out that the one thing that this reaction is going to be really good at is to form an epoxide. So first let me draw the epoxide. So what you'll notice here is the thing that I formed is this weird little triangular type of product here. It's like a cyclopropyl kind of thing where one of those carbons is an oxygen. Turns out this is a really, really useful intermediate in all kinds of different reaction types. And that is because there's so much ring strain there, this thing really wants to pop open. And usually in organic chemistry, when something wants to pop open, that's going to open the doors for some sort of reactivity. So we're not going to talk too much about how they're used just yet. But I will talk about the mechanism for this just because it's a good kind of more advanced arrow push that'll give us a little bit more insight into the way that we can push arrows around. So other things to add to the note card which are probably important. This is a type of syn addition. And as we talked about with syn additions, right, that means it has really particular stereochemical consequences. You can kind of see that here, the fact that this oxygen is just kind of added to one side. I honestly don't know how you'd add it to like 2 sides. There's not quite enough space in that cyclic structure there. But the important thing to recognize here is that this is a really particular reagent of a general class, right? This is a type of, let's draw it in red here so you can see it a little bit better. This is a type of what's called a peroxy acid. And one thing that organic chemists are really bad at doing is kind of just settling on one thing to call it in a reaction. So sometimes you'll see peroxy acid and they'll want you to do an epoxidation. Sometimes you'll see this specific reagent. Usually that's the one it is. Or even sometimes you can get the general form of a peroxy acid, which is anytime you've got some sort of carbon group attached to a whole bunch of different oxygens, right? To me, that always looked like ARCU, right? That's going to be our red flag that we're going to have to do some sort of epoxidation. And it turns out that I'll kind of show you the important parts of this, this condensed structure here when I do the mechanism. So the first thing I'm going to do is I'm going to show, I shouldn't do it in red. let's do it in black. We'll try to keep the red saved for mechanistic steps. So I'll show the structure of that in kind of a more expanded structure. A peroxy acid really looks a lot like a carboxylic acid with an extra oxygen, right? And so here we have that extra oxygen. It turns out that the peroxy linkage, just like, hydrogen peroxide, is anytime you've got an O directly single bonded to an O, usually that's something that's really easy to bust apart. It's a very labile bond. And so that's what we're going to take advantage of in the mechanism here. And so I'll kind of rotate around this six-membered ring, so I can kind of show this coming in from the top side, right? So what I'm trying to show here is like a flat cyclohexene. We're going to have what's called a pericyclic reaction, where we actually have this like kind of cascade of arrows that all kind of do everything in one step. So we're going to reach out and attack that, I guess, like more terminal oxygen there. That's going to cause our peroxy bond to break. And because this carbon would then be bonded 5 times if I didn't push anything else, we're going to see this bond reach out and attack that hydrogen. And then interestingly, that little carbon that developed kind of a transient positive charge, that is then going to satisfy the positive charge that would have developed there otherwise. And so what you'll see here in terms of the mechanism is that in one step with a whole bunch of arrows, I actually got to my product, right? And so this is called a pericyclic reaction. We'll see a couple of other these types through the term. But if you can push arrows like this, you really are doing quite well. And a lot of times, even when I do it on the board for the first time in a year, like I've done this a billion times, and sometimes I'll maybe attack the wrong oxygen. I'll kind of forget a couple of steps. But the good news is if you're really good at arrows and you can kind of follow where bonds are being broken and formed and positive charges are forming, it's very easy to do these arrow pushes. And actually, these kinds of arrow pushes are going to be really important in second and third term as we start to actually develop new mechanisms, right? You'll actually get problem sets where you have to figure out what the mechanism is. And the first couple are actually going to be on your homework for this week. So check that sucker out. Super useful reaction. I would make maybe a note card that has that written on it, maybe peroxy acid, this, maybe even like the more expanded form, because like I said, chemists can't decide on how the heck to show these things. Another really nice thing that we're going to talk about being able to do in kind of a synthetic protocol type of problem is the ability to selectively cut certain bonds. It turns out that alkene bond, even though it looks like it would be really hard to cut, this is a great reagent to use if you want to cut apart an organic molecule. And of course, there's tons of reasons that we'll want to do that, lots of which we'll talk about. This thing is probably more commonly known as ozonolysis. And that word probably helps you to kind of remember that you're actually going to cut some sort of set of bonds, right? Ozone, the compound, lysis, cut apart. Right? So let's take a look at how this works. This is a great example of where we'll talk about its mechanism quite a bit, but then in the second step, a lot of the mechanistic steps aren't as important. The outcomes are, however. So this is going to be kind of a mixed bag where we kind of have a partial mechanism, and then we'll talk a bunch about the second step of the mechanism and some important considerations there. The first thing we should talk about with regards to ozonolysis is the importance of recognizing that the second step is really important in terms of what product you form. It turns out both of these have ozonolysis, but there are two different reactant conditions that are present in the second step, right? And so you can just assume that we're reacting another one of these starting materials down here. This condition, where H2O2 is a prime example, is called an oxidative workup. So oxidative workup. Whereas this is called a reductive workup. And as I mentioned in one other lecture video, we will talk about oxidations and reductions specifically eventually in this course. So you just kind of have to take my word for it at this point that this truly is an oxidative workup and that is truly a reductive workup. But let's take a look at the product distribution. So the two very different products you're going to end up with really do depend on what the substitution pattern is on both of the alkene carbons. It turns out if you're like this carbon that doesn't have any H's attached to it, we really don't care. It turns out that the second step doesn't really matter. The second step is definitely going to matter though for carbons like this one where you can see that there's actually a hydrogen attached there. It turns out in an oxidative condition that hydrogen becomes an OH when subjected to the reaction conditions. And this guy right here actually will just be left alone in the second reductive condition here. So let me kind of show you in a little bit more detail what this guy looks like and also see if I can get rid of all that shade right there. So before we actually see the real mechanism of the ozonolysis, let's first talk about the differences in the product and also kind of the way that we can think about this a little bit easier than looking at in the mechanism. The first thing that I do is whenever I see ozonolysis conditions, I know that I am going to cleave or cut the alkene, right? That's what the cleavage refers to. And what we're going to do, and you might not be able to see this, but we're essentially going to put oxygens on both of kind of the capped ends of where we cut that sucker. So we're going to cut it and we're going to put a double bonded oxygen or carbonyl on each one. So I'll just kind of show you the product of the oxidative conditions, right? The one that really matters because that H is going to turn into an OH, and I'll kind of spread out the ring. So here's the product of the oxidative conditions. You can see here that that is the kind of the topmost alkene carbon has become just a plain old ketone. And then you can see that the other one here that I've kind of like expanded out is a carboxylic acid. It turns out if these were reductive conditions, which I'll show on the very next slide, that thing would, instead of being a carboxylic acid, would be an aldehyde. And the reason we care about that is because carboxylic acids and aldehydes are going to be groups that we learn about in third term. We're going to do very different things to them and end up with very different consequences. So there's an example of the reductive process right here. But I should mention that dimethyl sulfide is a really, really common type of reductive condition. There's other ones, like I think in your homework it might be zinc and HCl. So we'll kind of learn, again, once we start talking about oxidation and reduction conditions, how to recognize them. But in terms of just your first note card, I'd put that on there. That's kind of the most common one. And also you'll notice that in the product, instead of having a carboxylic acid, that H is pretty much left alone, right? There is an H attached there, and there's still an H attached there. I chose to show you what's called a ring opening. It could be made much easier if we just had a plain old, alkene double bond, right? That tether just wouldn't be there, right? So you could just kind of imagine it would just end up with a ketone and then a separate aldehyde. It's just that this is kind of most commonly done in like a cyclic system to try to impart some sort of stereochemistry in products. So what we're going to do now is we'll actually look at the mechanism, and we're really only going to look at the mechanism of ozonolysis because it's, again, going to provide us with a little bit of practice with arrow pushing and also with pericyclic reactions. So you'll notice what I did here is I made the starting material a little simpler, and I also only have the single step, just the ozonolysis. And so we'll end with kind of a weirdo product here. Then after the second step is where you get your aldehyde or carboxylic acid or ketone and all that other stuff. So we're going to just take a look at the mechanism. So the key to a lot of mechanisms is to be able to do a Lewis structure for your reagent. It turns out if I'm an ozone, I have a structure that's bent, and it's also interesting in that it's got both a positive and a negative charge in there. And so our job is to figure out where that bond is going to swing, right? This is a normal heterolytic mechanism. And a lot of students get a little confused, or I guess they get kind of tempted by this positive charge. and they think that that double bond is going to swing right out and attack that positive charge. It turns out that quite often, probably more often than that, is we're going to attack something next to a positive charge in order to get kind of a nice flow of arrows that we're hopefully going to be able to see here. So we're going to still swing this double bond out, but the initial arrow is actually going to attack that oxygen, which causes this double bond to just kind of satisfy the positive charge. That's a really common reactive motif, which is one of the reasons I like to show this mechanism. And so as a result of that swinging out, just like we saw in a previous example, that creates kind of a transient positive charge here. It turns out in pericyclic reactions, it's commonly the case that all these arrows kind of happen together. So the second that there's a little bit of positive charge, this negatively formally charged oxygen reaches in with its electrons, and we form something that looks like a 5-membered ring with oxygens. And this guy is typically called a molozonid type intermediate. Turns out a molozonid intermediate is not very stable, so it's not something that you could like easily isolate from the reaction conditions. It's not stable because of all these oxygen bonds, right? We've seen before that kind of peroxy type linkage is very labile and tends to break. And so a really interesting thing happens. It turns out that this double bond right here, or what used to be the double bond, actually cleaves temporarily in the following fashion. And what we kind of have is this kind of pericyclic mechanism within another pericyclic mechanism. The products here are actually two separate products. So now we've got our two products, right? And so you can see that these are cleaved apart, but they don't look anything like the final cleavage product. The important thing to recognize is that at this point, we've got the bond cleaved. It turns out that what happens now is kind of an oddball step. We're going to talk about the fact that carbonyl carbons, in the presence of good nucleophiles, it's really common that these guys get attacked. So this is kind of the first example of something like this happening. And the interesting thing is that the second that this is attacked, this doesn't just kind of hang out and go up to the oxygen, but actually goes and reattaches to the other part of this compound. And if you've practiced with arrows a little bit and kind of keep track of where bonds are broken and where bonds are formed, which is the whole reason we're kind of going through this, what you recognize is that you are going to form something that's got essentially a couple of oxygens in a 5-membered ring again, but now it's connected to these carbons in the middle right here. This guy is called an ozonid, otherwise known as a trioxylane. And I might have misspelled that, and hopefully you can even see it. But this is what you could isolate after that very first step. It's not incredibly stable, but it's something that you could actually isolate. And that's what those reductive and oxidative conditions actually work on. Of course, we're not going to show the mechanism of that because we haven't really talked about redox chemistry just yet. And it's really, quite honestly, not that important. We know that second step in this particular reaction. But this gives us a lot of practice in pericyclic arrows. It's something that we really should feel a lot better about. So here's a great example of it. So it turns out there's another way that we could do an oxidative cleavage that's a little bit easier in terms of like just kind of throwing a couple of things together in lab. But there are some problems with it, which we'll discuss as well. So let's start with our same simple starting material. And instead of doing an ozonolysis, what we're going to do is we're going to treat this thing with a really strong oxidizing agent that we're going to see over and over again. It's called potassium permanganate, KMNO4. You probably used it in general chemistry. And the other thing which we have to indicate is that we have very, very hot conditions, right? So this has to be hot and let's say acidic. Usually when you see something like that, by the way, sometimes hot is just abbreviated as a triangle. If you look at this thing and you see that somebody's really trying to beat the crap out of it with KMNO4, they're trying to do some sort of oxidative cleavage. And just as you'd expect, you're going to cleave this double bond into two different units of this. It turns out that in the case of KMNO4, you don't have any choice but to put an OH on that. There is no more mild, like in the ozonolysis case with reductive conditions. You kind of get a carboxylic acid or you don't. The problem is that with KMNO4, under these really hard conditions, yes, you can get to that. But the problem is that, as we're going to see by the end of second and third term, KMNO4 reacts with a ton of stuff. And so usually if you use it, you try to be kind of careful with it. So what can happen, which, is sometimes a reaction in and of itself, if you don't treat this hard enough and you keep your KMNO4 cold and let's say dilute, right? And maybe up here we should have added concentrated. It turns out that instead of cleaving a double bond, you can do what's called vicinal diol formation. And technically, those OH groups both end up on the same side. So one problem with KMNO4 cleavage is just this kind of side reaction. Sometimes you will actually want to get to the diol. And again, you're afraid that if you're trying to go to the diol, you don't want to go all the way to the carboxylic acid. So that's where the third reaction that we're going to talk about comes in, which is the treatment with osmium tetroxide. So let's go right to that one. So let's say we're working through some sort of reaction protocol and we see osmium tetroxide. This is a really common reaction for a really specific type of product. It turns out it's that vicinal diol that we saw before. So what we can do is just know that this thing forms a vicinal diol where both OH groups are projected in the same manner. It turns out that when we get to synthesis and we start using things like epoxides that you saw in a previous installment of the same video lecture, that's going to be able to be treated to give us these trans diols. This is a cis diol. One kind of common thing with osmium tetroxide that means absolutely nothing to you right now and probably won't for a while, it's super toxic. So usually what people do is you'll see some other kind of witch's brew type stuff in there with reagents that you've never heard of. NMO is a way to kind of reduce the amount of osmium that's needed so you can use the osmium catalytically, blah, blah, blah. Just don't be surprised if you happen to see that there. Another kind of random thing that is often thrown in is sodium bisulfite, and that has to do with kind of clipping off the osmium. This is another reaction which is, syn, so obviously this is a stereospecific. And also involves a syn addition. And just like we saw before, if we kind of take this six-membered ring and kind of lie it flat, what actually is going to happen with this osmium tetroxide species, which by the way is a really, really wacky looking organometallic, right? The second that you talk about something from this, the scary region of the periodic table, there's all kinds of weird bonding situations in there. But what happens here is that you reach out just like you normally would, and you undergo this, essentially the first step of this thing is you end up with this osmium salt, or I should say organoosmium compound, right? And so that kind of syn addition, just like we've seen as kind of a general theme, if you're going to undergo a syn addition, usually it means you're going to deliver the same thing to one face, right? At least in the case of a six-membered ring. So the reason that we need this craziness right here is in order to get rid of this osmium species so that we can then fish it out later and hopefully contaminate some sort of stream and end up with a third eyeball on your fish. But the important thing to recognize here, just a really good notecard reaction and is commonly asked about on the American Chemical Society exam and such that we're going to be taking. So let's go on and we'll see number 4. So this particular topic, I wasn't sure where else to put, and so I just kind of listed it off at the end of us talking about alkenes. One of the things that you'll start to pick up on is the presence of this word dilute versus concentrated, and usually it has to do with acids. Usually when you see dilute acid, usually it's going to be some sort of catalytic acid, and it's dilute because it's in an aqueous environment, right? And so really when you see dilute acid, it often means, at least in the case of alkenes, that you're doing some sort of hydration. So let's see an example of that. So here's a perfect example of where organic chemists are trying to confuse you, right? You see dilute H2SO4. And if you look back through all your reactions, you'll say, well, he never talked about H2SO4. Like, what the heck is that thing there for? Well, it turns out that's just a catalytic acid, right? And if you imagine that this thing is dilute because there's a whole bunch of H2O around, the real thing that's being listed off here, which I'll list in green, really what they're saying is you have H3O plus floating around. Well, we know what to do with H3O plus, right? We know that that means that we're going to do some sort of hydration. So it turns out the correct answer here is a Markovnikov hydration. The problem is that sometimes it's not dilute. Sometimes it says concentrated. Watch what happens when we have some sort of concentrated H2SO4. You'll notice concentrated H2SO4, right? It really has added the equivalent of an AB system where your B is actually that sulfate group, right? So this kind of reaction will become important when we get to synthesis, but only because this thing has some really spectacular properties. I don't want you to be confused by that, right? So it's kind of a dirty trick that organic chemists will often play. And what we're going to do is over the course of the next 3 terms is we're going to start to kind of generally classify reagents so that sometimes we won't miss the forest for the trees, right? Sometimes it's important to know what your tree is. Sometimes it's important to just kind of generalize and be like, that's just kind of a smokescreen. I'm just really talking about some sort of catalytic acid in that case. So be aware of this. There is, I think, a homework question where you do the same thing with acetic acid, right? So like if it's just plain old, really dilute acetic acid, you're going to end up with a hydration. If it's something with super duper concentrated glacial acetic acid, you might actually add like a carbonate group out here. So something to just be aware of. Hope that this list of random reactions comes in useful for you someday. Make sure you make those note cards. I'm serious about that.